All right, so in this video, I want to show you how you can use the Black-Scholes pricing model as well as the implied volatility in order to compute from an options chain these implied volatility surfaces, which look pretty cool and give you a bunch of info. I'm not going to be going over the interpretation of these surfaces. If you'd like, I can make a video on that, but this is really how to obtain them from an options chain. Okay, so what is this plot? Just what are the values? The z-axis is the implied volatility, which I'll give you a little recap on in a second. The time to expiration is simply how long before the option expires. Simple as that. And then the axis here is what's called the moneyness. And this is usually either given as K by S or S by K. S is the price of the underlying. So if this is a Tesla call option, this happens to be an Apple call option. Or a Apple call options chain, I should say. So S is just the price of Apple at the time that I obtained this options chain. Okay. K is the strike price of the option. And so the idea is that we take a bunch of different dates that the options will expire, and we look at a bunch of different strike prices, and then we pull the market price of those options, and we use all that info to sort of inversely solve for what the volatility is that satisfies that market price. And then once we do that, we simply make a plot out of the data. Okay, so just a very brief recap on the Black-Scholes pricing model. You have this is your formula for the value, theoretically, of a call option. S is the price of the underlying. K is the strike price of the option. T is the time to maturity in years. R is the risk-free rate. Q is dividend yield. And then sigma is the volatility. So we don't know the volatility, but we know these other 5 variables, and we also know the market price of the option. So we have 7 variables, 6 knowns, 1 unknown, and that means we can, in theory, solve for the volatility, which is implied by the market price of the option. Now, unfortunately, there's not a very good analytical solution for this sigma value, so we have to do this iteratively. Basically, we guess what the volatility is, we check what our output from the theoretical pricing model is, and then we adjust sigma until our theoretical price matches the market price. So my last 2 videos went over the implementation of the Black-Scholes pricing model as well as how to solve for the implied volatility, so I'm really not going to go over this. I'll zoom out a bit so you can just copy the code down if you'd like, but I would strongly recommend you check out my last videos on those. So here is the pricing model. Copy that down if you'd like. Solving for the implied volatility, that's what this function here does, and you can copy that down if you would like as well. I'll pause. And then this loss function is something which we use to update the sigma guess, and then basically from there, we just get the implied volatility. And that's all you need to know. So you don't need to worry too much about how to compute these things or whatever. That's not the purpose of this video. But if you're interested, check out my most recent video. Okay, so what do we need? Well, we need a bunch of these different strike prices, times to expiration, and market prices for the options. And this is simply called an options chain. So I have for you the options chain for Apple that I obtained a few days ago. And here's the relevant info. We need the market price of the option, okay? We need the date to expiration, which is, or well, I should say the expiration date, and then I've converted that over here into the date per expiration. All I've done is I've taken the number of days to this date and then divide by 365. That's all. Of course, you need to know if it's a call or a put option as well, and that's really it. So you need the K here, T for the time to expiration, and the market price of the option. Okay? Then what we do is we just loop over this data frame and we compute all the implied volatilities. So I save, or initialize, I should say, an array for us. First one is for our implied volatilities. This one is for the moneyness parameter, which again is just S divided by K. And then DTE stands for days to expiration. Okay? And at the time, the market price was around 245 when I pulled this options chain. And yeah, so what we do is we loop over the data frame and we grab the strike price, we grab the time to expiration, and I already have these, the R variable set here, and we're leaving Q equal to 0. I should have specified that R was already defined up here. Let me just define it really quickly. R equals 0.045. And then we can go ahead and run this. So it's going to go through, compute for us all of the implied volatilities over these. I have about 100 options in this options chain. And you can see it's done. So now how do we plot this? So we have basically 3D points, right? We have points with an X, Y, and a Z value. So how do we make a plot like that? Well, we're going to use matplotlib for this. So here I just set up the figure, specify its size, its dimensions, all of that. The important thing here is you need to do this projection equals 3D so that we can get a 3D surface. And then we use this plot trisurf function. Now what plot trisurf does is you have to think about it. An array of 3D points does not have a uniquely defined surface. And so this is one specific algorithm that sort of connects those points in a very intuitive way, and it gives you very reasonable surfaces. So it's very useful for plotting things like this, implied volatility surfaces. Okay, then there's just, all of this is really just to make it look nice. So I have some colors, aspect ratios, pixel density, a color map, all of that. Here I set the labels. I just name the labels. I give it a title, and I give it our initial viewing angle. And then I just do plot.show. So all you really need is these first few lines here. And then you could do something like plot.show, and you'll be all set. Feel free to add the other stuff if you want the fancy labels, though. And this is the plot here. In Jupyter Lab, so this is a Jupyter notebook. I don't really like to use it for plotting 3D plots because you can't drag them around with matplotlib. So what I've done is I've just converted all of this into a Python script, and I just ran the Python script. So you can do the exact same thing if you want, and that's actually what I would recommend you do. And here is your plot. So basically, again, we take all of these strike prices, all of these dates to expiration, and then the corresponding market price for the call option. And then we go backwards and solve for the implied volatility. Take it, throw it into this plotting algorithm here, plot.trisurf, or plot_trisurf, and you get a nice volatility surface. So you can interpret this in a number of different ways. Anomalies in the surface are usually points of interest. Regions where it's otherwise low volatility and you get a big spike might be useful for writing an option. Or regions where it's sort of deceptively low. We don't really have many of those in this specific plot, but those might be regions where you would want to buy options, right? And so that's the idea. Yeah, I'm not going to, again, go into the interpretation of these. That's a whole nother topic. I'd be happy to make a video on if people are interested, but that pretty much does it for this one. So I'll wrap it up there. I hope that you find this useful. Comment down below if you have any questions or you need help with the plotting, and I will try to get back to you as soon as possible. So I will call it for today and say thank you very much for watching, and I hope you have a good rest of your day.